Okay. Good evening. This is we are part of team 3. My teammates are Akshaya, Rajakumar, Siddarth, Sadeesh Kumar, and I myself, Shreyas, Jaikumar. And this is just a quick introduction, and this is just a demo video pertaining to Lab 5 pipeline data path on the net FPGA. Thank you.
Now I will be demonstrating the working of the intrusion detection system on the net FPGA node. For this, I will have to download the bitstream file onto this net FPGA node. So now I'll show all the registers that are associated with the IDS. So as you can see, there are like 4 registers: matches, pattern high, pattern low, and command. So this pattern high and pattern low are the registers that will be set according to the pattern that we give to the that we want to find. So now I'll set the pattern to A B C D E F G H E F G. So now as you can see, the registers have been loaded with the values like the higher part and the lower part. Now I'll check if ping works in the nodes. So I'll do RKD and then ping one of the nodes. So as we can see, ping is working. Now I'll try to send a string of the same pattern ABCD from one node to another node by setting one node as a server and another node as a client using netcat. So, and you can try to see if matches is being updated. So on this node 1, I'll initiate the server. And then in node 0, I'll be initiating the client and then send a pattern ABCDEFG. So I've initiated a server here. And then I'll go to the client side and send a packet, send a string ABCDEFG. So it has been received. Now we can check the matches register to see if there are any updates. So as you can see here, the matches register is being updated by a value of 1. So it has been incremented. Now I can send it again and check if matches is being updated. I just send it again. Now you can see it has been incremented by a value of 1 again. Now we can also try to do this with using the iperf commands, but the difference is in iperf we cannot send a string like a single string, but we have to send a file which contains a string. So here I've initiated the iperf server, and here on the client side I'm sending the file which contains the string to the server. So this bat file.txt contains the single string ABCDEFG. And I'm trying to send it. So it has been sent now. I'll go and check the matches register value. So as you can see, it is incremented by a value of 11. So this is because the file is being sent multiple times because it's UDP, and the number of times the matches have been found, it has been updated. So the IDS is working, and as we can see from the matches register that is being updated.
So the first part is building an ALU. And although in the pipeline data path in this current lab, we are not testing the ALU, we just went ahead and built, we just built a basic schematic of the ALU in Xilinx ISE 10.1. And as you can see from my screen over here, we came up with a simple code for the ALU, and it is given that we must include the following instructions, that is operations, arithmetic, add, subtract, logical and or XNOR, bitwise from a bitwise point of view, shift left logical, shift right logical, and comparison as well. So as you can see from my computer over here, in order to denote these 8 operations, it happens through a 3-bit opcode. And by just implementing a simple case statement, these all the 8 operations that I just specified above are being covered. So this is the source code for that. In some time, I'm going to shift to my another computer, that is my mini PC, and show the outputs that we obtained after having written a test bench as well, that the correct operations for happens for the ALU. And yeah, so now I'm just going to quickly go through all the source codes built by us. So that's it for the ALU. And the second part is building a register file and the memories. Okay. So it is given that we have to build at least 4 registers, and we went with 64-bit because the recommended, because the net FPGA data path is also 64-bit wide. And this is the source code pertaining to the register file. And as you can see, it is very self-explanatory. It's very intuitive as well. So these are all the respective inputs that is needed. The reason why 3 bits are denoted for the first register address, the second register address, and the write address is because of the instruction format that is provided in the PDF or in the LabFi, instruction manual. And based on that, we denoted this. However, the entire write data is a 64-bit data, and the output is also 64 bits in total. So that's it. So yeah, all these are self-explanatory. If reset signal is true, then it's going to be all the 8 locations are going to be initialized with 64 zeros. Else, based on what the address is, that is going to be the data is going to be assigned correctly. So yeah, this is pretty simple. And then they have given that it is mentioned that we need to use the core IP. So in Xilinx IC 10.1 under sources, when we add new source, we went ahead and chose the IP core generator. And based on their specifications, that is, it is given that we have to generate a block RAM based dual port synchronous memory with 64-bit wide data and 256 entries. So basically that's 8 bits address. So that will be our DMEM data memory. And our instruction memory is 32-bit width and 512 depth. And they have given a choice of also considering 16-bit width and 1024 depth, but we went with 32-bit width and 512 depth because that perfectly suited our ISA. That's our instruction memory. So I'm just going to quickly open so as you can see, there's a bunch of files over here pertaining to DMEM and IMEM. This is because of the fact that since we used, as I specified, we used core IP generator, right, to generate all these. As a result, there is a bunch of files, but the most important files are the .xco files, which will go into the source folder in the NetFPGA projects in Fedora, and the .ngc file will go into the synth folder. Similarly, the same thing for IMEM as well. So just going to quickly run through this. This is basically a black box. So to be honest, this is just generated for us, and I'm just quickly going through that. So we gave the exact specifications as what is being provided in the PDF manual. That is choosing, as I said, right, 64-bit wide data, 8 address, so 256 entries. If we need write enable or not, write first, write first or read first. Basically, in DMEM, you're not using the port B at all, so it's just zeros. Or in other words, it's don't care. So based on all those mentioned specifications, accordingly in Xilinx and the core IP generator, we went ahead and put those specs and thereby instantiated the memory modules. So this is the code for dmem.v, and similarly, this is the code, the black box code, which is generated by Xilinx itself after having put the respective specs it just generated for us. Okay. Moving on to the pivotal part, building the pipeline data path. Okay. Now I'm going to open the pipeline data path code. Okay. So from the figure, we have 1, 2, 3, 4, and 5 stages. Basically, the third stage is a dummy stage, and we believe that, and we know that that is where that's technically the execution stage, and that's where the ALU will come into place in the successive lab. But for now, it's just a dummy stage. So I'm just going to, I'm not going to do a line-by-line explanation of the code. That will take a lot of time. I'm just going to quickly run through the whole code. So basically, it's just we are, instantiating a module named pipeline underscore data path with all the respective input and output wires. Then comes the PC. So if reset, it's just 32 bits in total. Else it will be incremented by 1. It's not byte addressable, it's word addressable. Ergo, we are just incrementing the PC by 1. Then just a sec. Yeah, actually, I'm just going to open it here. So yeah, this is the code. As I said, so we went through till PC. So this is, so 9 bits for the instruction memory address because 512 bits in total, right? I just told about that. So this, as I said, is based on the provided instruction format. So 1 bit. So we are preloading our instruction memory with the said, we are preloading the instruction memory with the said signals. Therefore, this is like a much simpler way to test our design for now, as provided in the PDF format. So 1 bit goes for the write memory enable, 1 bit is for the write register enable, 3 bits is for the first register address, 3 bits is for the second register address, and 3 bits is for the write register address. And this is basically, boilerplate code for pipelining. So this is just going to propagate from stage 1 to stage 2, stage 2 to stage 3, stage 3 to stage 4, and finally stage 4 to stage 5. So I'm just going to quickly go through that. So yeah, basically this is, again, as I said, boilerplate. If reset, everything is going to be 0. Else, the assignment happens accordingly. So from the first stage to the second stage, that's the pipeline stage registers captures that, right? So that is being reflected over here. This is the register file module instantiation. Stage 3, as I pointed out earlier, is just a dummy stage. But we didn't bypass that stage by making our code, and thereby, we didn't want to optimize our code. We just stuck to the design provided. It's just a replication of what I said earlier. So it was stage 1 to stage 2. Now it's stage 2 to stage 3. And yeah, no other changes. Similarly, for stage 3 to stage 4, the write address is being propagated entirely through the pipe until the last write back stage, and then that is being connected to the register file because that has to be 4 cycles late in order to ensure synchronization, so that the write happens to the correct register address and not the instruction that enters the pipe. So that won't reflect the correct return value, right? Yeah. This is something which I pointed out earlier. It's just it's not used by us. Port B is not used at all. Yeah, cool. So that's the skeleton code for the pipeline underscore data path. And then comes, okay. So this is basically a small test bench code that we wrote. And now in a minute, I'm going to shift to my another computer and show the simulated results. The instruction memory that we preloaded is exactly based on what is being specified in the PDF manual. So it's a total of 6 clocks. So the end visibility will happen in the 7th clock cycle, end of 6th, beginning of 7th. So so address 0, load address 0, register 0 is equal to 0 of the data memory into register 2. Load address 0, register 0, which is equal to 0 of DMEM into register 3. There are 3 no-ops. And finally, we are storing the instruction. We are storing 4 into memory address 4. So, as you can see from the respective waveform, clock cycle 0, clock cycle 1, clock cycle 2, clock cycle 3, clock cycle 4, clock cycle 5, clock cycle 6, clock cycle 7. Clock cycle 7, store 4 into memory address 4. So this is clock cycle 7. We are storing 4 into memory address 4. That is being correctly reflected over here. In the middle, it's just a bunch of no-ops. And in the start 2 also, it's loading address 0. Register 0 is equal to 0. So basically, it is also going to be 0 only into the respective registers. So I'm going to go backwards now. So as you can see here, clock cycle 7, 4. 4 is being correctly loaded. Everything happens on a clock by clock basis. PC is getting incremented. Yes. Which is integrating the pipeline into the net FPGA. So here, basically, the key changes that we made is we went, of course, we had to make the respective changes in project.xml and in IDS.xml. First, I'm going to quickly cover the XML files. So in the XML files, what we did is these are the software and hardware registers that we are using. One software register called PC, because we are not, we are incrementing only the PC and not the clock cycle, because of the fact that the processor versus the net FPGA, from a timing point of view, the net FPGA is orders of magnitude faster. And therefore, by the time that all the 7 instructions have passed on into the net FPGA, not even one instruction, probably just one instruction would come out of the Perl script. So there will be major timing mismatches. So we are not going by clocks, we are going by PC incrementation. So that is why we have declared a software register for the PC and 6 hardware registers. Debug PC, reg 0 is 1 register, and low is from the middle to the LSB, whilst up is middle value plus 1 to the MSB. By the same logic, for the second register, low and up works in the same way, and debug instruction for the instructions. So this is the changes that we made to the config/XML file. Based on the aforementioned changes, of course, from lab 4 to lab 5, all the unnecessary parts we did cut out. Just a sec. We have specified all the registers accordingly in terms of bits. So now in the net FPGA, after the synthesis being passed successfully, we got the register mapping in the memory. So these are all the 7 registers that we are using. And accordingly, it is being declared in the respect, and accordingly, these are the respective memory address pertaining to this. And this is needed because when we do IDS regs, reg read, reg write, we need to provide the memory location accordingly, right? So yeah, so those are that. So apart from this, yeah, we didn't make any changes. No changes are required pertaining to here, reg write, reg read. There were a bunch of commands and codes pertaining to pattern match, pattern high, pattern low, etc. And since that is not needed for our particular project, we deleted all that. And yeah, so basically what the global variable here is being declared is being mapped accordingly to the respective um, register. So debug PC maps to, I mean, this is just boilerplate stuff, right? We are just doing a register read on $IDS underscore debug PC register for debug PC. And yeah, by the same logic for all the other registers. Debug PC, reg low up, reg low, reg 0 low, reg 0 up, reg 1 low, reg 1 up, and instruction register. Now my teammates are going to show the working demo in the NetFPGA wherein like correctly the data from the instruction memory is being written onto the correct location on the register file, the preloaded instructions. So that will be demonstrated by my teammates.
The previous sim was not practical enough for a NetFPGA application. So while checking a NetFPGA, it'd be hard for us to like exactly see what the values are at any particular clock cycle, because I mean the whole cycle will be done within like six clock cycles. So we won't be able to see and track what instructions going on, what's the register value we're getting for our small test bench case. For that, so not like uh, not have that condition, we just like have a small modification to the other code, which is like implementing a PC, giving a PC as an input value. So we just did modifications for that. So instead of like automatic incrementation for every clock cycle for PC, we just have an input for PC and did modifications around that. So again, I'll just show you the test bench code for that also. It's like, yeah. So yeah, we're just incrementing the PCF for every 20 seconds in simulation perspective. And in our NetFPGA implementation, we'll just do PC write for all, reg write for all the PC values. So I'll do a small sim for this condition. So yeah. So yeah, this is our, so yeah, this is the sim result. So if I zoom in, you can see the values are like at when our instruction 930, we're getting an output of 4, which is in our registers, which is what we need for our test condition we have used. And yeah, I can see the instruction being based upon the IMM we have given. And we are using the COE file seems perfect for the IMM also, as you can see here. So this is actually following for input in PC instructions as well. as well as the automatic PC, which is supposed to be the actual thing of a closed processor. Yeah, just moving on to the FPGA. Hi, so I thought of just running over both the synthesis for both the operation, the actual one and the one we did with PC input. So I'll just run the simulation for the actual, I'll show you the files and run simulation for the actual one with the PC input and just everything running based up in the processor on its own. So I'll show you the files we are having. These are the files we're having. Pretty much same files will be used for our other sources, except like one modification just in the pipeline data path and in also in IDS and IDS.v and IDS.xml, which is our like master files. Like, so yeah, this is actual one code. Just like for this, I'll just do a synthesis for this. I mean, pretty much same stuff for IDS.v. We just don't have in the input for IDS.v. We don't have an input called as PC, and then we don't have an input in IDS. Yeah, XML and include also separate input PC, which you'll see in this. It's not there. This like runs on its own. So I'll just do a quick synthesis for this. Yeah. So yeah, we are able to like do a synthesis. I actually did a synthesis earlier and have like kept a file over here, which is yeah, this is a bit file I got, and we tried for implementing this on NetFPGA, but we just aren't able to like track the outputs in time. Just too fast with the clock cycle being like the whole process getting over in 7 o'clock, so it was hard for us to like track. So we just went with the other approach of giving an input PC and implementing it. So yeah, just go on the next one, which is the actual one we are implementing on our NetFPGA. Oh yeah. Um, so yeah, I'll just go over the SRC files again and then show you the main one. Okay, so sorry. Yeah. So the it's pretty much same files will be used. I mean, the only modification, as I said earlier, will be in the pipeline data path, IDs.v and IDs.xml. I'll show you what the changes are there in pipeline data path. I mean, yeah, as I said in the sim for this, just we just comment out the whole thing and implement it. It's having a PC as an input here. I can see again here. It's having a PC input. Similar like changes are done for IDs.v and then yeah. So yeah, we're having a soft register for PC, which is like our input. And so yeah, just run our synthesis for this also and show you that part. Just for yeah, see, so I think since it's done pretty much. I mean, all are pre-saved synthesis, so pretty much it's quite very quick here. Yeah, so I just got the bit stream earlier and just like loaded it over here. This bit stream for PC input piece with an input for bit stream. For this, I'll just implement this on the net FPGA. So yeah, finally we just want to implement the PC, which is sorry, it's the bit stream which has an input PC in a net FPGA, which I'll just do in the next part of the video. So in the NetAPG, we did a modification for and made a new Perl script for pipeline. So I'll just show you the Perl script once and more. This is a pipeline Perl script. So the regs are basically what we get from our reg underscore defines underscore 5 for from the register folder. From there, we just have one reg, and then we are doing reg write and reg read, and also we have an all regs, which is like shows all the values for pertaining to all the register values, all the output values basically. Here, this is our file, and now I just download the bitstream file which I've got for my got from synthesis. I'll show you that. So yeah, the bitstream is downloaded successfully. Okay, so I'll do like reg write for PC equal to 0 and PC is and 0 x. Yeah, sorry, 0. So just reset it up and yeah. So yeah, I mean RPC is equal to 1, the instruction will be around this is the value in our IMM also be given for zeros, the entry is going to be 4 zeros, 4 all 5 zeros. It's kind of working now. So it's like maybe change the PC, increment the PC and see. So yeah, 406, which is again the second value, I think, which matches with us. Like, and for 2, yeah, the yeah, yeah, it's a no op condition again, matching with our value we need. And 3, yeah, again a no op. 2, there'll be 3 no ops, so a second no op. And 4, again a no op. And 5. I think this will just get the output. Yeah. So for instruction we're getting the right instruction just to load to the register file. So yeah, register files are getting updated with the values for both and we're getting values in both our register files now as 4 and 4, which matches with our same results with here or here. Yeah. So yeah, 93 and 3 all zeros, we're getting 4 and 4 values. And yeah, as you can see, the PC code is 0, we're getting the same values in SIM and in native VGA. So yeah, our like design seems working fine. Uh, yeah. So yeah, thank you very much.